Good evening, everybody. Thanks, Noah, for organizing this and for arranging this. I'm very happy to be here tonight with you guys. Sorry. So just a little background. I've been working for SIDN for the last 3 years. Before that, I used to work for TU Delft. I was a research director of the cybersecurity group. No, I am in a cybersecurity group, a guest, 1 day a week. But I used to work there as a postdoc, and I did my PhD in 20 at another university here in Enschede. Quickly over SIDN, if you have a .nl domain, this is the company who maintains the .nl thing. We have 5.8 million domain names, 2.8 are signed with DNSSEC, which is an extension for DNS that allows to actually guarantee that your record's valid. We get like 1.4 billion queries a day on our servers, or the DNS infrastructure that we run. We work on a bunch of products for better security. We're now a size of 100 employees. When I joined, I think it was 85, but it's been growing kind of fast. You're not for profit, which is a very cool thing, because I like to work in a place kind of you don't have the market pressure and stuff, but it's very nice. And I think last year, 1.5 years ago, we acquired another company from Rotterdam. It's called Connectus. Maybe some of you guys know. They do like it's a AAA authentication kind of services. And well, we have like almost 1,300 registrars. These are the companies that can actually sell the domains to you, so you can register that. All right, I work at the lab, so it's pretty much research. And research and industry would have also very strong academic ties. And the thing we do there in a company is research, is applied research. It has to be directly applied for the things we do or we run. This is us. 3 more people are going to be joined soon. We have internships, so if some people want to write the bachelor thesis or whatever there, we also have positions to write there. And there's a bunch of products here. I mean, I can share those slides here later if you guys, there's all those links there. But things we do has to have some contribution to the society or to the business that we run. And there's a bunch of products that we run. If you're interested in IoT, some of my colleagues have developed this Stream product, which is just a firmware you run on a small box that can have your Wi-Fi in your house, only for IoT devices. You can see all your devices are communicating to the internet and block them. So it has a web interface. It's kind of cool, super nice. And there's like tools for measurements. You work a lot of internet measurements, so these are open sources. But anyway, let's get started. DDoS, denied service attacks. I mean, let me just sense the crowd here. For the first presentation from Karina, I sense a lot of people here do JavaScript, and then I would assume you guys doing front ends, right? Am I correct? Or back end as well, because JavaScript is everything nowadays. It's very different from when it started. But who runs here a website or web application? So it's good. That's great. And who has DOS protection on your website application? Oh, that's not so many, but we got one here. All right, who knows its own DNS setup of this website? Do you know? Oh, that's very good. I mean, how many authoritative name servers do you have? What's the time to live record of your TTL? Like if you have a domain like example.nl, you can set a value for it. It's called TTL. It's how long whoever gets the answer for your, like where's example.nl, how long they could actually keep that in cache. And that's very important. I'm going to talk about tonight. So it's something, if you're worried about the DOS, this is extremely important. Background. This is the command utility dig on Linux. You can see the pointer. Yes, that's great. So if you, let's say, dig a wikipedia.org, you want to know what's the IP address of Wikipedia. Then you got this IP address, your browser can go there. That's because on the internet, routing works at the IP level, but humans are pretty bad to remember this, so you need to create DNS to give you easier things like this. So this is the direct mapping. But who gives you this answer in the end? Who knows the answer for your question? Is what we call authoritative name servers. These are these guys here. If you want to know who are they for Wikipedia, you have to tell this command, dig ns.wikipedia.org. And ns defines who are the domains, the name servers who actually know the answer. Now, here we have a user that wants to go to your application that you develop. You're making millions of this stuff. It's called example.nl. So, a lot of people put protection here in example.nl, but to get to example.nl, we have to go to DNS first. Someone has to say, hey, where's example.nl? This is the first step here. And the authoritative name server, which is the DNS server, which is going to tell you the answer, say, hey, you got to go to this IP address. And he goes, all right, cool. So I'm going to then send the HTTP GET request to the application or whatever you're running. And a lot of people protect here, but not so much here. But that thing, to get here, you need to first fix this. Yeah? And what would happen if this would fail? Could this actually happen? Well, it has happened. The biggest, at the time, was the biggest analysis attack ever. Dyn DNS was a huge DNS provider, has been bought by Oracle after the attack, which is funny because they got really destroyed and gave a lot of publicity so people got to know them, and Oracle just bought them up. You remember the Mirai botnet? Was a botnet, IoT botnet, got infected, tons of cameras, start to send legitimate requests to actually the authoritative servers of Dyn, and a lot of clients of Dyn, which are like the New York Times, a bunch of others, they were clients of Dyn, so people went to the servers of Dyn, hey, where's New York Times? Where's Etsy? Where's Spotify? Where's whatever? They could not get an answer because the servers who knew the answer were under DDoS. They were not available. And I mean the DNS servers, everything on HTTP level of Spotify, New York Times was fine. It was fine and up and running. There was no problem. The problem was on the DNS side. That's the thing I said here. This part was down, but this was fine. So do you understand the importance of DNS in this process here? If it goes down, everything else goes down. And then what's happened? Like there was a DDoS. It was a major attack on the core infrastructure of the internet. All these people went down, or partially down. And as I said, the sites were up and running, but nobody could reach because they could not resolve the domain name. So, I mean, we work with DNS at SI10. We run .nl. We have a bunch of authoritative servers, and we're very scared about the DDoS. We get the DDoS sometimes. We don't like it. But I work on the research. I don't work in operations, so I have no access to operation, which is amazing because I don't have a lot of responsibility, by the way, that thing. It's a lot of pressure. So I do research, which is fun, but there's different sorts of pressures. And we started a project, it's called SAND project with the University of Southern California and University of Twente, and from Amsterdam also, NLNet Labs. Probably you guys, some of you know them. They are great. They're one of the best in the world. They do DNS software, first class, open source in Amsterdam. They're amazing. They do have you heard of Unbound DNS software? Bind? There's Bind, which is DNS. It's this is the number 2 in the world. It's real good. So we started a project to say, hey, can we evaluate design choices of DNS? Just see how we can engineer now for DDoS, because these DDoS are getting bigger, cheaper, more frequent with these IoT botnets. So we started this project, and the idea is not only do research for academic reasons, that's fun, but we want to do research to improve our operations. We want to, in the end of the research, say, hey, operators, we recommend you to do this and that because of these large-scale measurement results. So you can improve your network. And I'm taking DDoS here. I'm taking DNS because it's the thing that I work with, but it can be any application you're talking about here. And the problem with DNS is it's a very juicy target. If you take this core infrastructure service like DNS, it's going to take a lot of people down at the same time. So the question I have in this case that I'm going to present here tonight is what DNS has done. Actually, DNS is a juicy target and has been attacked over and over and over. And you don't hear that much on the news about the attacks on DNS, unless things go really bad with Dyn. But usually, people DNS just service it off. It's not that easy, but you kind of get away with that. And how did they do that? So if you look at the, you guys know what's RFC, request for comments on the Internet IETF. The IETF, the first DNS IETF, the one RFC for DNS, is more than 30 years old. So this thing is old as hell. So they had a lot of time to build a lot of redundancy into DNS. And how did they do that? And the answer is layer after layer after layer of redundancy. And it's very important for people like you guys who develop applications to be aware of this. Not only to design to over-provision in a certain level, but very different levels for the worst case scenario. Because your clients are not going to be happy if things go down. You know that very well. So we wrote this paper. I'm a background academic, and I work in industry, but it's industry, but the academic component helps a lot in that. So papers is just a motivation for that. It's all open source. And what we did, it's looking, the servers will know the answer. They use a technology called Anycast. We're going to be talking, how can you configure them? How can you nobody knew how they would react when there's a DDoS. I'm going to explain here. So we just look into that. So let's go back to this case study. There's an application here who wants to know example.nl, and you go to the internet, some magic happens, you get an answer. That's the kind of jobs you guys do. That's all you need to know about DNS. That's, I mean, if things are working fine, that's all you need to know. You don't need to know about anything else. But there's a lot of things behind that. So let's dissect a little bit this cloud here, how does it really work. So usually in a computer and operating system, there's some software called Stub Resolver. It's a piece of DNS software that runs in your computer that can ask these questions. And usually, you cannot ask authoritative servers directly. You ask a DNS resolver. Probably you guys, a lot of you know, use this IP address, right? For like 8.8.8 for Google, right? In your IoT devices at home or whatever. No? Do you guys check resolve.conf sometimes in your network? Don't know where your queries go to? You might want to look into this because people do a lot of profiling based on that. They can know a lot about you, just look at your queries. But anyway, when you get an IP from your computer at home, you also get DNS servers saying, hey, it comes together, like say, if you want to resolve queries, send to these IP addresses. And they call recursives, that's the R's here. And they, on your behalf, are going to talk with all these people above here, root.nl, assembly.nl. There's the process called recursion. I'm not going to go into that. But they're going to do all the hard work for you to get the answer. So there's this middleman here. And what you're going to be looking here is the people who know the answer. They can run Anycast. And how we can have redundancy per multiple layers. So on the green layer here, what people actually do, it's something, not only, they don't put only one server, because that would be a classic single point of failure. You all know about that. They run multiple name servers. So that's defined by, like the example of Wikipedia that I had. Let me see if I can go back here. They had 3 authoritative name servers that can give you the same answer. It doesn't matter which one you ask, you're going to get the same answer. But also, these guys here, they run something called IP Anycast. How many of you heard about Anycast? Yeah, cool. So Anycast, one IP address, it's like you get one IP address, usually you think of a physical location that's hosted, right? I mean, but actually, Anycast, you can announce this IP from, you name it, 500 places in the globe, in various different places. So just the same IP announced with BGP from multiple locations. And so that's what they do for the authoritative side. For the recursive resolver side, the guy who's going to help you to resolve the answers, they also do Anycast and caching. So when you ask a query to authoritative, you get an answer, it's going to be in the cache for the TCL value. But let's get to the details. So let's say a user has to go to a root server. There are 13 root servers you can ask your questions about the root zone, the top of the DNS. So instead of having only one, they have 13. And within this 13, you can run IP Anycast, which allow, this is one IP address, but it can announce from, let's say, 33 different locations across the globe. In each location, you have like multiple servers, meaning one IP address, 500, 1,000 IP addresses in reality, servers in reality. That's called Anycast. And this is all redundancy, layer after layer. And this is like all the DNS servers that are authoritative for the root zone, not for the NL, but for the top of the root zone. They're like more than 500 locations across the globe. This is the map. You can check it out online. And what we have done is to use internet measurements to analyze a big attack back in the day, 2015, against the roots. It was 35 gigabits per second for 2 hours. It was 2 different parts. But I'm not going to get into very much details here. There's all in the paper. You can have a look. But my idea here is that you guys who develop applications, you can use internet measurements to diagnose how well your application performs. And that's very important because you know probably much better than I, that's like if you have a web application running, if there's a delay of 100, 200 milliseconds, customers are going to buy less things from your site. So DNS has play a big role in latency, and that's one of the things we work. We want to reduce latency for users. So there was this attack, and how many of you guys know RIPE NCC in Amsterdam? They do RIPE Atlas. It's a measurement platform. But anyway, we can actually use their measurements they collect for free. There's a download for free all the data, big data on the internet. And you can look at the 13 servers on the internet that got attacked. So I think it's a lot of information, but everything that goes down here is when the attack happens. So if a user would go to broot, which is one of the servers, to get an answer, he would not get an answer. The server was down here and here too. And the gray line here is when the attack happened. And this is the number of users who got an answer. So everything was fine, and then the attack started. This one went down. This one, eRoot, 50% of people were happy, 50% were not happy. Some were just fine, and others were not attacked. But that's the first layer, that's the IP layer. But if you look at and if also we can look how long did it take to get us answers. So if you would go to kroot, during the attack, you would see like instead of latency of 50 milliseconds, you would see like around 30, you would see around 50. But others we went from 60 to 300. So you see application gets lower during the DOS attack. Some you would not even get an answer. So you can actually be seeing that. In another layer, it's like this other graph here shows this Anycast sites of this layer of the different places across the globe for K-root, how they fail independently. And that was the contribution that I studied. You see, one IP is attacked and you have Anycast, different places fail differently. It depends a lot on BGP. But like this is just an X-ray of the attack, pretty much I'm showing. And when you get like to the K-root in Amsterdam, for example, or Frankfurt, K-root has three machines in Frankfurt, server 1, 2, and 3, and they fail differently. When there was a DDoS, which starts right here, two of the servers went down and one went up. And I don't know why, but my hypothesis is like the load balancer here said, whoa, I'm under attack. I'm just going to send all the traffic to one server only because I cannot forward this thing. And in Japan, in Narita, it's the opposite. They just try to distribute evenly across the street. So you got to be aware of these things if you develop web applications, because these things may actually impact your performance. So the lessons in this thing here is like internet measurements allowed us to do a lot of diagnosis. In this case, allow to diagnose how each layer of DNS behaved. And for people who develop applications, they can use RIPE Atlas. It's an open, free platform. You can start measurements from anywhere in the globe to measure how you perform. So, I mean, I'll share the slides, you can have a look at that. But I think with something more closer to you guys might be the resolver side. And we did another study, again, looking into but also concerned about DNS, how DNS can help you from attacks. I'm going to present this next month. So here, the cool thing about, let me go back to this. I think I showed this figure before. But like, these are the servers who actually know the answer. We call them authoritative name servers. If you want to ask about examiner.nl, this guy would know. But this is you wanted to know that. But you have to ask the recursives resolved in the middle, the Google Quad 8 or Quad 9 or whatever. And they have local caches. So when you ask a query for examiner.nl here, this guy is going to put this thing in the cache. Right? It's going to, hey, because these don't have to go all the time there. I mean, you say, keep for 1 hour. 1 hour will be fine. Things will not have changed here. So he can keep there, which is going to speed up a lot of the performance. And the question is, like, can you trust caching during those attacks? Because if this thing goes down, the only thing protecting a user to go to your website if the DNS is down is the caches here. And can you trust that? So that's the question we investigate in this paper. And there are things you could do. You could model, simulate. It's very academic and boring. What we did is like measure in the wild 15,000 vantage points from different places in the world. Measure it, wide-scale, with RIPE Atlas for free. We did that, and we simulated DOS attacks. So first thing, if you have a DNS server and people are getting answers, and you wanted to know if your server is actually caching correctly the answers, if they really cache. And it turns out that 70% of the cases, this is what the graph shows, DNS caching works just as expected. So if they ask you example.nl or your web application.nl or whatever, if you say keep the record for 1 hour, 70% of the time they're going to keep it. Even sometimes if you change your DNS configurations, they're going to take 1 hour or two to propagate. It's because of this TTL thing, because it keeps in their caches. So that's the explanation for that. And this is a design choice of DNS engineers to say, let's put some data or some knowledge in the resolver side, so if things go down, they can still resolve it, and also to improve performance for the user, because keys cache, everything caches faster because it's local. So 70% of the time it works fine, and also good news, 30% of the time, 30% doesn't work. And the question that I had was like, all right, what happens if there's a DDoS? These caches are going to help during a DDoS attack, and I simulate a bunch of DDoS attacks. We can do that with IP tables, it's super easy. And I'm going to choose, there are many, but I'm going to just choose two scenarios to explain you here. The first scenario is the doomsday scenario. All your authoritative name servers go down, pretty much like dying. And, well, dying didn't go, everything went down, a lot of it went. But like, nobody can resolve your domain name anymore because your servers are down. So how long, then you're on the clock. You know, clients are going to be very angry at you. But whoever has asked the questions before, like, if you're a popular website, probably you're in a cache of somewhere out there who asked the question for you. And the question is how long you can trust the cache, how long you're going to protect users, given the right answers. So what we have done, we have sent measurements from 15,000 vantage points every 10 minutes, right? And the blue here is okay, things went well. But after 9 minutes, what I did, I just switched off my authoritative name servers. I just did not respond anymore. And I look at the users who are actually getting an answer. And my TTL value was 1 hour, meaning whoever had an answer, the first round was just fine, so they could get all the answers here. But all those people here, they could keep this answer for an hour. And you see that, it started to decline. This kind of stable until here, but after that, started declining. And after the cache expires right here, nobody gets an answer. Very few people. There's a reason, because some people serve the answer past the TTL. It's called serve stale. It's not standardized, but some do it. But what it matters for you, develop applications here, is like, if the DNS goes down, your clients, a lot of them are going to keep the records. You're going to be able to resolve your domain, even though the server goes down, as long as your TTL is valid and as long as their caches are filled. So this shows like whoever designs DNS protects users from failures, and that's why you don't see a lot of things in the news, because caches are protecting users, especially from popular websites. And one thing is to design this like in a code or in a model, but the other thing is to have this DNS software deployed for 30 years across the globe, various different vendors, various different versions. You cannot model this thing anymore, it's too complex. So what you have to do is measure in the wild to observe how things go, because it's too complex to model. So 35 of 75% of the people were actually served, even though they could not get an answer from alternatives. Caches helped a lot. And another scenario that we had was like, I find this one particularly cool, because this one is the case that your server, the DNS server, will drop 90% of the incoming traffic. So 90% of the queries are not going to get an answer. And you see that here's all normal. I'm not doing any DDoS here. And here is simulated DDoS. And out of my 15,000 probes here, roughly 60%, the blues one here, I get an answer. And even though they're actually dropping 90% of the packets. You think, how is this possible? Right? It's mind-boggling. What are they doing? Well, there's a consequence for that. It takes longer. So focus on the green line here. This is just how long does it take. Usually it will take like 100 milliseconds, but then you see like 500 milliseconds and get an answer. People get nervous here and angry, but but at least they're getting an answer. They could go to your application that I know, website later, and do their business, buy whatever they want to buy, whatever. And at this line here, I switch on the servers again, and very quickly the clients get an answer again. But the message here is like, even at 90% of the packet loss at the DNS would be like a big DDoS, most of the clients get an answer. And in this particular case, here the cache was 30 minutes. So they were either getting a cache answer for the cache or somewhere else. And the somewhere else was the alternative servers, because 1 in 10 queries go there. So 1 in 10 are successful. And if you run a DNS server, if you were under DDoS, we also observed this. This is the number of queries you were getting in our servers. And when the DDoS started for the same experiment, you see the recursives. They're like, oh, I send a query, never get an answer. What I do? Try again. So you see, like, we observe like 8.1 times more traffic during the DDoS. This is normal traffic. This is not DDoS traffic. This is legitimate traffic. Because people are like, I'm going to get an answer. I'll try. And they're doing the right thing. So, which means if you're running your DNS infrastructure and it's under DDoS, you're not only getting DDoS attack, you're getting 8 times more traffic from legitimate traffic of people struggling to get an answer. And so people usually in DNS say, well, we're going to over-provision our servers by 10 times. Well, good luck with that, because 8.1 is already legitimate traffic. What are you going to leave in for actually the actual attack? So this one was like, whoa, this was mind-boggling. So this has actually implications for operations in the company, the people who run DNS. So the lessons we had from the redundancy layer here, because it's very important for dependencies. It's like, be very careful on how you choose your TTLs and your records and your applications. The longer you set them, the longer they'll be in the cache, the longer your clients are going to be, if there's a DDoS, the longer they're going to be reachable if they're in the cache. So be careful about that. Now we are investigating how to actually set this correctly because there's a lot of interdependencies. But the problem is like be careful. A lot of people put them very short, like 1 minute, because they can very quickly change them. But you gotta be aware if this is DDoS, you're gonna be unreachable. And you're gonna get a lot of friendly fire during DDoS, which is a bad thing. Anyway, so I think I can summarize that. So the DNS, like I think I talked a bunch of this stuff here, but what I'm trying to say is like one of the core servers of the internet, we actually get a lot of DDoS attacks lately. They're very cheap now to do. You can actually buy online. They call booters. These are sites they serve what they call stress network testers, which pretty much is euphemism for DDoS. It's a very just target. So you can get DDoS anytime. I mean, schools in Friesland, Jesus Christ, they get DDoS every week. I don't know what these kids in Friesland do, but they DDoS their schools all the time. It's crazy. And what interests me is like all these moving parts of the system, when they come together, how do they behave? And what you can learn from that, engineering-wise. So I think that's it. Thanks for attention, man.
So I had a question. So sometimes I go on my ABN AMRO banking app, and I see like, hey, we're currently experiencing a DDoS attack. Is that then DDoS hammering the auth server, or is that on a DNS level? Like specific example, or maybe you can.
I remember that ABN case a couple of months ago, right?
Yeah.
They yelled at this guy from Brabant or something. He said it was fun to do the DDoS on the bank, right? And and it was his second DDoS apparently. He got ABN down, ING. I think that one was not on DNS. I think that one was actually on the web service. Yeah, but it depends. I mean, it depends a lot on the attack. I mean, if you're careful design enough, you can do a lot of damage because what people don't realize, sometimes the same name servers, same authoritative name server, they are responsible for thousands of domain names, like Dyn. So that's the risk of collateral damage. If you have your site there and your neighbor gets attacked, you're on the same server, you go down, man. You're not a victim, you go down. Yeah. So there's all this dependency, and that's also the market. Some people want to pay less, and they don't care about shared hosting, whatever. But like, this is all intertwined. But anyway, I think that their answer, ABN, I think was a direct attack to the bank actually, because now you have this. I'm not sure. I don't remember how big it was the attack. I'm not sure if they actually talked about it. But now this IoT botnets, it's easy to get terabit level attacks. So there was one attack in the US, the biggest so far, 1.7 terabit per second. I don't know who can handle that. I mean, it's 1.7 terabit per second.
Terabit, okay.
But and that's the ones they make public. I mean, I remember like in 2004, Rio Olympic Games was 2014, 16, right? They had like 600 gigabits per second at that time for months. Wow. Akamai was behind it trying, because now they have the entire DNS protection industry. Akamai, Cloudflare, they only sell you protection. So there's a new business development around the DOS. So so it depends a lot on the attack.
Okay. I have a few questions.
Yeah.
What is the popular expiry time of this cache for TTL? You made examples about 1 hour or 30 minutes.
So we have, so here it's like 1 minute. This one is.
This is longer. Okay.
This is on a DDoS. It's just like how cache works. Half an hour, 1 hour, 1 day. Depends a lot. So CDNs, they do like here. Anything on CDNs, they do like 1 minute. Mm-hmm. If it's a name server, it's a record of a DNS server, they do like 1 day. Mm-hmm. But it depends a lot. I mean, actually one of the reviewers in the paper asked that. My colleague computed the number, but I don't remember by heart, but it depends a lot. So we see everything. You see like from 1 hour, 1 second to 1 day.
Even 1 day, okay, no, that's more why I'm curious.
It's like, there was like cyber hacktivism, that's a different thing. But there's just random thing. It's very hard to trace back on the internet who did what. Mm-hmm. But for example, this one against the roots were analyzed, nobody knows who did it. Mm-hmm. Okay. That's the problem. It's very hard to go back. And even the security agencies, they found those who did it, they cannot prove because it's all classified data. It's all secret. So like you say, well, we know it's the Chinese, but how do you know? Oh, then because we hacked into the networks. So they're gonna tell you that.
Yeah, that's true. That's true.
Yeah. All right, so I think we're good. Thanks a lot.
All right.